inverse trigonometric functions. So here we're going to look at the inverse functions of sine, cos and tan. So we'll start with sine. Let's go ahead and draw up our sine curve. So we're going to draw in y equals sine x. We're going to get something like this for y equals sine x from minus 2 pi to 2 pi. And because we're interested in our inverse function, we're going to draw in the line y equals x. And it's going to be something like that. And now we're going to draw in y equals inverse sine x, which is just a reflection of sine x about y equals x. And doing that, we're actually going to get something like this, where instead of oscillating around the x-axis, inverse sine oscillates about the y-axis. So on our original graph, we were going from minus 1 to 1 for the y-axis, which means for our inverse function, we're moving from 1 to minus 1 on our x-axis, and this would be the point minus 2 pi, and this would be the point 2 pi. But we can see that the inverse function we've created is not a function, because drawing a vertical line through would actually cut at infinite points on the graph if we extended this forever. So we need to limit this function so it will pass the vertical line test. And there's also infinite places we could limit the function, but the place we're going to limit the function is actually in between here and here. And those points there, so let's draw the function out again, just so I can make it more clear. So the inverse function that we'd like to deal with actually looks something like this, where that ranges from 1 to minus 1 on the x-axis, and it ranges from pi on 2 to minus pi on 2 on the y-axis. So what this means is our domain is that x has to be between minus 1 and 1, and our range is between minus pi on 2 and pi on 2. So with an inverse function, we get a domain that was equal to the range of the original function, and we get a range that was equal to the domain of the original function. And this ends up being our inverse function of sine x. So this is y equals the inverse sine of x. So let's go ahead and do the same thing for y equals cos x. We want to use it to sketch the inverse cos of x. So it is going to be similar. So we've got 0 to 2 pi there, then we're going from 0 to minus 2 pi. Let's go ahead and draw in y equals x. And now we can reflect it about the y equals x line. And we're going to get something like this. For our inverse cos graph using that reflection. But again, this is not a function because it doesn't pass the vertical line test, so we have to limit our function. And again, there's an infinite places we could limit the function, but we're going to limit the function from here to define our inverse function. So again, let's just draw that separately. And we're going to get something like this for our inverse cos x function. And again, its domain will be going from 1 to -1, but our range is actually going to go up to pi. So let's just write in our domain is going to be when x is between -1 and 1, and our range is going to be from when y is between 0 and pi. And again, for every inverse function, domain and range switches from the original function. All right, let's now look at our tan function. So we're going to look at y equals tan x, and we're going to use that to help us get y equals inverse tan of x. So for our tan x, we actually get something like this, where we have asymptotes at pi on 2 and minus pi on 2, and that graph repeats in both directions, but this is all we need to graph our inverse. So let's go ahead and sketch in y equals x. And doing this reflection, well, always with an inverse, any vertical lines become horizontal. So our asymptotes become horizontal. And then doing the reflection, we get something like this. And let's just go ahead and draw that separately so we can fully see what's going on. So we have an asymptote going through pi on 2, and another one going through minus pi on 2, and we have our function looking something like that. So our domain is actually all real x, and our range is that y is between, not equal to. Now y is between minus pi on 2 and pi on 2. So you can see if we just kept extending our original tan function, it would have created not a function for our inverse tan.